Welcome everybody to WestGrid's webinar. My name is Alex Razumov. I'm a WestGrid training and visualization coordinator, and today I'll be speaking about YT, using YT analysis and visualization tool, both on your machine, on your own laptop, and on clusters. YT is a standalone library for volumetric visualization, analysis and visualization, and it was written specifically to work with multi-resolution data. That is data that comes at, on many different subgrids at different levels of resolution. And initially, it was written as a visualized tool for ANSO galaxy formation code. So those of you not familiar with ANSO and galaxy formation simulations, so if you run a galaxy formation simulation, usually it's a very large box, cosmological box, and there you turn on various physics, and things start to fall into gravity wells. So basically, galaxies, clusters of galaxies, and so on, formed under gravitational forces, and then they form very small objects where interesting things happen. So where actual galaxies form, and you want to resolve these objects. So that's why you want to place high resolution grids or meshes into the regions where you want to get more detail. So typically, the simulations have hundreds or thousands of subgrids of variable resolution, and a lot of grids are placed into regions where you form galaxies, where interesting things happen, and so on. So YT was written specifically as a tool to visualize that, and in recent years, it was actually adopted by people from other fields as well. So the goal of this webinar is not so much to show YT to astrophysics folks, but to show it to a more general audience, because people in astrophysics, they already know about YT usually, but a lot of people from other fields are completely not aware of it. So it's good to learn new tools always. I just want to remind, I'm getting background noise from somebody. Please make sure that if you're not asking questions, mute yourself. Okay. Thank you. So YT documentation is really excellent. Everything I'm going to show you today you can also find in documentation. And YT is not an interactive tool in the sense that, unlike traditional three-dimensional scientific visualization packages like ParaView and Visit, where you can just load an object and then explore it interactively with the mouse, zoom in, rotate it, and so on. In YT, everything you do from the Python shell. So it's a Python library. There is an ongoing project to write a standalone GUI tool for YT, so it's called ViewYT, but as far as I know, it's still very much work in progress, and right now, mostly the way you use YT is from the command line. So let me give you very quickly historical context for YT. Astrophysicists have been running numerical multidimensional, so first 2D and then three-dimensional simulations for many decades, actually. So in the 70s, people started doing 2D simulations. In the 80s, 3D simulations. In the 90s, people started writing AMR, adaptive mass requirement codes, multi-resolution codes that I mentioned. And for all this time, they needed some good volumetric visualization tool. And there were no, so a few decades back, actually, as early as early 2000s, there was no good tool for doing that sort of visualization. So that requires, that is open source, multi-platform, that is scalable in the sense that you can actually run it on a cluster in parallel to analyze very large data sets. And lots of researchers in astrophysics, they wrote their own tools. So the tools like IFRIT, FTT, and a few others, some of them were open sourced. Other researchers just use existing general purpose tools, so things like MATLAB, Interactive Data Language, IDL. The problem with IDL and MATLAB is that they're commercial and they're not really designed for multi-resolution data. And because they're commercial, they come with lots of limitations in the sense of where you can run them, how large you can scale these visualization and rendering and analysis tools. So YT was started around 2006, 2007. It was written by Matthew Turk, a grad student at Stanford at the time. And he also open sourced it. And it quickly took off. And the reason why it became so popular, actually, there are several reasons. So first of all, it was written in Python. And that means that in Python, you have access to very high-level functions for data analysis. It's very intuitive, very easy to learn. I mean, it was written very well, and also since it's open source, lots of other people could contribute to it. And right now, if you go to the YT website, you'll see 128 listed contributors to the code. Okay, so it understands a lot of different data formats, 20 or 30 different data formats. So I listed them here, and a lot of these are astrophysical codes. Not all of them, but the majority of these are astrophysical codes. But the point here is that YT can actually read any type of spatially discretized data, whether you have data on continuous mesh, on particles, on unstructured meshes, on curvilinear meshes. And towards the end of my presentation, I'm going to show you several examples how you can read data that is not understood by one of these built-in readers. So YT is a Python package, and that means that it's fairly easy to install it. So here I show several examples. If you have Conda or mini Conda installed so Conda is the Python distribution for scientific computing, you can just type Conda install -c conda forge repository YT, and it'll install it. You can also use the Python installer, so the traditional pip tool, or you can simply download the source code and then compile it and install it into your Python installation as well. And that will give you a working copy of YT, and you can optionally download data sets from YT, the YT website. So here I give links to several data sets in the middle of this slide that I played with, and I'm going to show some of these in today's webinar. So all of these are not particularly large data sets. They typically are of the order of several hundred megabytes, so you can actually download them and visualize them on your laptop. And if you want to use YT inside a Jupyter Notebook, the YT folks actually put a very nice set of Jupyter Notebook tutorials. But to download them, you actually have to download the source code behind YT. So the link at the lines at the bottom of the slide show you how to do that. You'll need to download YT source code and then go into one of the subdirectories and start a Jupyter Notebook. And that will open, they have some like 5 or 6 different pre-filled notebooks, and you just run individual cells, and it will give you a lot of useful information. Okay, so here is how you would load data into YT. So this example is from ANSO simulation, so once again, galaxy formation code. And in this case, it's not a cosmological simulation, it's a standalone galaxy, so they just took a volume about 1 megaparsec on a side. So a megaparsec is a million parsecs, and a parsec is 3 light years. So a volume 3 million light years on a side, and then they turn on physics, gravity, and interesting things started happening. So here we're loading, first of all, we import the YT module into your Python shell, and we'll load one of the time steps, so time step number 30. And then it loads it, and then we can optionally print statistics. So we'll say ds. ds is a handler, is a pointer to the data set that we just loaded. So we'll say ds print underscore stats, and in this case, it will print the basic statistics of this data set. So what we have here is how many? We have 173 subgrids, including the base grid. So the base grid is the main grid from which we're starting. So the base grid in this case is let's see, it is 32 cube, and then we have quite a large number of subgrids, high resolution grids, and you can see this table lists their levels of refinement, number of subgrids at each refinement level, then number of cells, and then effective resolution. So if you just take the third root of the number of cells, you'll get the effective resolution. Okay. So you can optionally examine data. So in ANSO, there are lots and lots of physical fields. So some of these are 3-dimensional fields, some of these are just lists, 1-dimensional lists, some of these are just numbers. So ANSO output contains 55 fields, and you can simply type ds field list, and then it will list the fields that are already inside the data set. So when you load the data set, you actually load all these fields. And optionally, you can use derived fields. So the ANSO reader has rules for calculating about 350 derived fields. So if you want to list all fields, so the data set fields plus derived fields, you will do something like JS derived field list, and that will give you a huge list of 405 fields. And if you want to see a rule for how a specific derived field was computed, you'll just type ds field info, the name of the field, and then get source, and that will tell you the exact mathematical formula behind this field. So also notice that, and this is specific to Enzo reader. All fields have tuples, so they have two words. So for example, all creation time or Enzo H1 density and so on. So the reason this is done this way is because there are lots and lots of fields in Enzo, and they are just grouped into several categories. So there's an all category, Enzo category, IO category, and so on. But in principle, you can actually write a reader, or some readers might have not tuples but single name field names, single word field names. All right. So here's how you would examine data. You can just type ds, for example, domain width, and that will tell you the size of the computational box. In this case, it's a 3D box in code units, so it's 1, 1, 1. You can type ds domain center, that will give you the center of the box, so 0.5 in each dimension. Left edge, right edge, dimensions, so it's a 32 by 32 by 32 cube. You can type ds parameters, and that will print out the various parameters that are specific to these simulations. So for example, one of them is going to be star maker minimum mass. That is the mass of a gas particle above which you can convert the gas particle into stellar particle. So in this case, 8,000 solar masses. You can also print domain with the box size, not in code units, but in physical units. So for example, you can print it in kiloparsecs. It's you can see it's 1,000 kiloparsecs, so it's a million parsecs on the side. You can print it in astronomical units. You can print it in centimeters, kilometers, anything you want. So it's very nice that the notion of units, not just for length, but for all physical variables, density, pressure, whatever, is built into YT. So it's really, really easy to query any value in any unit you want to use. You can also examine the AMAC hierarchy. So this simulation, actually, let me go back a few slides. So this is the which simulation is isolated galaxy. Let me just go back to this slide. So the isolated galaxy data set, so sample data set, has 32 cube base grid and 8 additional levels of refinement. Okay. So let me go back to examining subgrids. So here we have, I will simply say print out index, DS index number of grids, 173 grids in total, maximum level of refinement 8. Then we can actually, so ds.index dot grid levels will give you a list of levels of refinement for each of 173 subgrids. So grid dimensions also for each of 173 subgrids, you get dimensions. So the base grid is 32 by 32 by 32, and so on. So grid left edge for each subgrid right edge, how many particles are hosted by that grid. So particles in Enzo simulations, particles are dark matter particles. And you can select, for example, the first grid, the column on the right. We're selecting the very first grid, so it happens to be the base grid. And you can print out its dimensions, so it's going to be 32 cube. And then separately, only for this grid, you can print various numbers. For example, the left edge, the right edge, its level. So level is 0. You can see that the base grid obviously covers the entire box, so it goes from 0 to 1 in each dimension. You can also print its children. So children means the subgrids that fall entirely within the grid, and that have and to which this subgrid has pointers. So similarly, you can print all grids get a pointer to all grids at a given resolution level. For example, all grids at level 8 will create a pointer called GS, and then GS of 0 subsetting will give you the very first of these subgrids on level 8. And then similarly, you can print any property you want for that subgrid. And then the last line just shows you an example of how you can print an actual three-dimensional field. So there's a field called density. And then in this case, I'm printing subsetting one layer of this density, right? So using the usual square brackets in Python. And here the output is going to be a two-dimensional layer. Okay. In density in units of grams per centimeter cube. Okay, so that's all I want to say for printing the basic statistics of your data. Let's now see how you can visualize data. So lots of examples I'm going to show you with Enzo data, but towards the end of this slide or of this presentation, I'm also going to show you some examples how you can read non-Enzo and generic data, generic Cartesian meshes, and so on. So you would import. So this is the entire code on the right, and then on the left you see the visualization. So we'll load the data. Then optionally, we can print the redshift of this data set. And then we simply pass the data, ds, pointer to the slice plot routine, so yt.slicePlot routine. So we're asking it to plot a slice of this data set, multi-resolution data set, in the XY plane. So the normal is the Z-axis. We're going to print the slice of density. That's the field. And then you have many different ways of specifying the center of your slice. So in this case, we're using max. So max is will give you a slice through the highest density point in the volume. So optionally, you can specify the explicitly XYZ coordinates, or you can say the center of the volume, or minimum or maximum of any field you want, and so on. So you can see that it gives you lots and lots of flexibility. And then so we'll create the slice, SLC, and then we'll just say slc.save into a PNG image, and then it will save the slice that you see on the screen into a PNG file. So if you work, I prefer to work from the Python shell inside my terminal, but if you work from a Jupyter notebook, then you can use commands something like slc render or slc plot. I can't remember now. I played with it last week, but I don't remember. So if you prefer Jupyter notebook, that command will give you a plot right inside the Jupyter notebook behind you, just below your cell, which some people like, some people don't, but you have such option. So you still have interactivity from the command line in the sense that you can type in commands and then save an image, and your image will adjust to whatever you want. So for example, you can zoom in, you can pan around the image. There are a few other commands. So in this case, I'll go back to the previous slide. There is a dense structure in the middle, a galaxy cluster, and we want to zoom in on this galaxy cluster. So what I'll say is SLC, so our slice, zoom by a factor of 5. And then again, save the slice, open this image, and then the image on the left you see is the image you get from this command. So there are several other ways of controlling the zoom level or the box, the window size that you're seeing in your image. So for example, you can import the megaparsec unit from yt.units, and you can simply set the width of your window of your image in megaparsecs, in physical size. And that will give you, in this case, 10 megaparsecs, and then you just save it. Or you can also, so the last example shows, yeah. So when you create a slice is SLC is a handle, right? So it's a handle, it's an object that contains your slice, and lots of functions are built into the namespace of the slice. So for example, zoom function, the save function, and so on. And of course, you don't have to create an SLC pointer to the slice. You can just do everything in one command line. So Python lets you do that easily. So in this case, the very last commented line will let you create a slice from scratch from the dataset ds. So density going through the highest, the slice through the highest density point in your volume. Size of the box is 20 megaparsecs, and then you save it into an image 2b.png, and as you can see, the entire slicing procedure is all in a single Python line, which is really nice. Okay, you can also ask YT to plot more than a single field at a time. So in this case, you'll just, instead of passing the name of a single field, you pass the name of multiple fields as a list. So in this case, I'm passing the names of density and velocity magnitude. And I'm asking also a similar, a slice normal to the z-axis through the highest density peak. And then I can change, here in the second line, I'm changing the color map for the velocity plots. I'm just switching from a default color map to a Kamai color map, and then I just save it, and the save command will save both images as 2 individual files, and then you can see them on the left. So you can see at the bottom you have, so at the top you have the density plot, at the bottom you have the velocity plot in a slice, and you see that around the central galaxy cluster, the velocity is actually very high, but you don't know whether this is, I mean, it's a very high speed, but you don't know where the velocity vectors are pointing. So it'll be very nice to show directional velocity. And you can do that very easily with velocity annotations. All you have to do is just say slc.annotate velocity without any arguments. And in this case, because you don't supply any arguments, it will just annotate both plots, and it will put this nice three-dimensional velocity arrows onto both density and velocity plots, so you can actually see that you have an infall, gravitational infall into the central cluster. And then you just save the images, both images, with a single slc.save command. Okay. So let's take a look at another data set. This is the isolated galaxy data set. So before, in the previous plot, I was looking at, let me see, I was looking at this was a cosmological simulation, and now we are looking at an isolated galaxy simulation. So here we're asking to plot density in the XY plane, now going through the center of the volume. The size of the window of the plot is 15,000 parsecs, and then we just save it as an image. And again, I do it in a single command. So this is the disk. It's a spiral galaxy, small spiral galaxy disk on. So you can actually see the galactic spiral arms. And then if you want to see it edge on, all I have to do is just change the orientation. So instead of the Z normal axis, you specify different axis. So in this case, actually, sorry, before we go there, you can also annotate grids, right? So you just add the annotate grid command for this slice, and it'll show you the nice AMR, adaptive mesh refinement, nested grids, where you see that where you have spiral arms, more grids are placed there to get better resolution of the spiral arms. And then what I was mentioning before is that if you want to have a different orientation, so in this case, you want to take a look at this galaxy edge on, you just specify the normal vector. So the normal vector is the x-axis, and it'll show you the galaxy edge on, and you can see there's some feedback from supernovae, and it's just a very nice picture that you get in a single command. So this is all I'm going to show for slices, and now I'm going to jump to projections, unless there are any questions about slices. All right. So similar to a slice plot, there is a projection plot command. So in this case, we are starting with the same data set we saw in the previous slide, the isolated galaxy. And then, so ds is the pointer to the data set, and then we pass this data set into the projection plot function. Now we're doing projection along the z-axis. We are projecting density. So, and we are projecting using the integrate method without a weight. So basically, you have a three-dimensional density that is measured in units of grams per centimeter cube. So if you project it along one of the axes, the image that you get is going to be column density measured in grams per centimeter squared. And then we save it as an image, projection1.png, and then you see this image on the left side, and you see that the units for our projected quantity are actually correct. They are grams per centimeter squared. So this is just simple integration without a weight. So in some cases, you want to plot another quantity that is mass weighted, for example, or weighted by another field. So in this case, let's plot temperature, mass weighted temperature. So basically, mass weighted temperature is the ratio of the integral of density times temperature along the line of sight for each pixel, divided by the integral of density, well, divided by the column density integral. And then all you have to do is you're still using the method integrate. So now you're passing the field's temperature, integrate temperature with the density field. So weight field is density. And then again, you specify the width, the orientation of, so the normal vector, and then the file that you want to save it to, all again in a single Python command. And you can see that the velocity it ranges quite a bit. So it goes from roughly 100 degrees to several 100,000 degrees. So this probably 200,000 degrees Kelvin, this mass weighted temperature. So in some cases, you also want to, when you're integrating, actually, when you're doing the line of sight, you go through the line of sight for each pixel. You want not integration, but you want to pick up some unusual feature. For example, the highest value along each line of sight. And that is useful because you can very quickly identify unusual regions. So for example, let's pick up along each line of sight, let's pick up the highest temperature. And this will give you a plot like this. So what you do is you specify the field temperature. There is no weight. And then the method is MIP, and that will give you the highest temperature. And you can immediately see that in this region, so northwest of the galaxy itself, of the disk itself, there is a very hot region. And obviously what happened there is you have feedback from a supernova in the simulation, and the hot ionized gas from the supernova, which is tens of as hot as 20 million degrees Kelvin, it just blew into that into that region, and that's where you have this very hot region. So you can actually see that you can identify it very easily with this projection plot. So obviously this is not a physical quantity, but still really, really useful if you want to quickly scan the volume for unusual features. So finally, you can also do off-axis projection plots in YT, and for that you would not use the projection plot function I showed you before. Projection plot function cannot do off-axis projections, but there's a nice function called off-axis projection that will let you specify the normal vector and then to your projection plane, and then all quantity, well, the quantity that you're plotting is going to be integrated along that normal vector. So in this case, we are going through the center of our simulation volume. We are projecting density. So we're just integrating density without a weight. So resolution is 600. That's the resolution of the image that you want to get, so 600 by 600. And then the width is the portion of the box, computational box that you are sampling with this integration. And you also specify the normal vector. And now, because the normal vector is not parallel to one of the main axes, you see that instead of seeing the galaxy edge on, we see it at a slight, roughly 10-15 degree angle. Okay, and then so the output from this image is not a plot. From this function is not a plot. It's actually an image. And then there are a number of routines to write this image to a disk. So, for example, you can use write projection routine, or you can use write image routine. So the main difference between these two is when you use write image, it will not give you a color bar, whereas write projection will give you a color bar that you see on the left-hand side. And then you can optionally specify the label for the color bar, and so this is grams per centimeter squared, the usual column density. Okay. So this is all for projections, and of course the most interesting part is volumetric ray tracing. So this is where YT really shines. This is what you usually see on magazine covers. Very nice three-dimensional volumetric renderings, and of course volumetric rendering is much more demanding computationally because you are rendering with a transfer function. So it's more floating point operations. And right now, my understanding that it's primarily done in software, so you can actually do it on a CPU as opposed on GPUs. There is also a version of YT that is currently under development that will give you OpenGL rendering on a GPU. So I have not tried it, and I'm not sure how close it is to final, well, to actually release, but it's there. So in the near future, you'll be able to do this rendering, volumetric rendering on GPUs as well. So here's the code. Now the code is a little bit bigger, and the reason for this is because you have all manual controls you want. But of course, the code, these are optional controls. In a few slides, I'm also going to show you a volumetric rendering code that is much, much smaller, only 2 or 3 lines of code. So let me walk you through this visualization so that you know what sort of controls you have. So here, while loading in this case, it's a cosmological ANSO simulation, so ANSO 64. Then we set up a scene for volume rendering, and then we pick up the first object in the scene, and the object is the data field that contains the data field that you're going to render. So there's actually a single object in this data set, but it's just the way it's coded is you still have to select the scene and then the object in the scene. There's just a single object. And then for this object, so the data set, you specify the three-dimensional field that you want to integrate through. Then you're going to see that optionally you can specify the scale. So we're going to use the log scale. And the reason for this is because the cosmological density varies over many orders of magnitude. So you actually, the top plot here, you see from 10 to the minus 31 to 10 to the minus 26 grams per centimeter cube. So next, we start building the transfer function. So this is the part where you really want to spend time playing with it, and it gives you lots and lots of controls, and you can have fantastic pictures if you just invest a little bit of effort into building the right transfer function. So I specify the bounds. I'm going to only include densities in this range in units of grams per centimeter cube, and then I use the color transfer function to set up my transfer function, to which I add 2 Gaussian peaks. So I add a red spike and a cyan or a blue spike. So the red spike is going to be centered at logarithm of density 10 to the minus 28 grams per centimeter cube. So I specify the width of this Gaussian on the logarithmic scale, and I also specify the height, which is the signal, so the strength of the RGB, red, green, and blue filters, and also alpha. So alpha for the red spike is high, it's 1, and then the alpha for the second sine spike is only 5% of the red one. And the reason for this is because if I specified much taller Gaussian peak, I have lots and lots of cells in my volume that have those smaller densities, and my picture volume rendering will be completely overwhelmed by the cosmic web structure, so you will not see any red signal at all. So that's why I want to have the smaller alpha for the sine peak. And so I put the sine peak into into densities that correspond to the more extended cosmic web structure. And then, so here I finish building transfer function, and optionally I can just say printf, and that will tell you exactly print out the way you set up this transfer function. And then I need to apply my transfer function to the source. So I'm simply saying source.tfh, that stands for transfer function helper, is .tf is equal to my transfer function. So basically, this will fill in all the blanks. So everything that you don't specify will be using the default values. Everything you specify will be using the values you just set manually. So basically, you apply the transfer function to your object, and then optionally, you can print the transfer function itself, so the top plot on the left here, and then finally say save into the file volume.png, and then it will save a file. So the second argument, sigma clip, is there to make sure that you don't get any extra bright pixels. So if I reduce that number, let's say to 2 or to 1, then I'll get lots of very bright pixels, and the simplest way of that is just simply introduce a floor that will cut off very bright pixels. Or alternatively, you can modify a transfer function, and that will also achieve the same result. So as you can see, you have 2 peaks, and then you have information in the volume rendering from these 2 densities as well, and you have a fantastic plot. So this is for manual controls. We actually set up the 2 Gaussian peaks by hand. So alternatively, what you can do is you can replace these 2 add Gaussian lines with a single line add layers. And here we're simply asking YT to add 5 layers using the Arbor color map. And these layers, and that's all you do. Just use the code from the previous slide, replacing the add Gaussian lines with the add layers. And when you do printf, it will actually show you these 5 layers that will be used for volumetric rendering. And the way it's set up in YT is you see these what it's called. Well, you see these steps, so they are increasing. Actually, you see four of these. So the 5th one is very small, so that doesn't show in the transfer function plot at the top. So you have these 5 steps, and information alpha for these Gaussian peaks on the left, so smaller density, the alpha is much smaller. And the reason, of course, for this is because there's so much more signal from these low density cells that if you don't use smaller alpha, it will be completely overwhelmed by these low density peaks. And you want to see the range of densities. So that's why you use the transfer function in setup this way. And this is, of course, specific to these galaxy formation cosmological data sets. If you use your own data set, which is completely different, then probably what you want to do is use the add Gaussian function by hand. And the output of the volumetric rendering you can see on the left and at the bottom. Really nice picture. Right? So this is quite different. These 2 pictures are quite different from the typical volumetric rendering that you see in packages such as ParaView and Visit. And the reason for this is because we're not using continuous transfer functions. Instead, we're using these step Gaussian functions with a distinct, very narrow Gaussian peaks. But of course, if you want, you can also have a continuous transfer function. So here's a slide showing exactly that. We define a function that sets a linear transfer function, so it just shows as a log curve on the log scale, but it's a linear function. And then you pass that linear function to a map to color map YT function when you set up the color transfer function yourself. And then you get this kind of fuzzy picture that you normally see when you do volumetric ray tracing, play with the transfer function, let's say ParaView, right? So the point here is that you can have as much control as you want, and depending on the transfer function that you choose, whether it's a continuous one or a discrete one, you'll get very different results. So this plot shows you how you can use defaults. So in this case, the entire code for building the picture on the left is shown on the right. So here we'll load the data set, we'll create a scene, and then we just save it as a volumetric rendering. That's all. No other controls. And in this case, YT just did everything automatically, so you just used all the default transfer functions, and you still get a nice picture, although, of course, you don't have as much manual control here unless you add additional lines. The point here is that if you don't want code load, you can actually do this volumetric rendering in just a few steps. So I haven't mentioned that this volumetric rendering is actually quite CPU intensive. So these renderings take about 20 to 30 seconds on my laptop because, well, they're costly. But you can parallelize these renderings on a cluster, and in a few slides, I'm going to show you how you can do that. So you can also move the scene object, the scene camera around. So there are different routines in YT that let you move the camera. For example, you can move the camera around the central object, and so essentially the central object will be spinning around a normal vector, let's say vertical axis. You can move the camera to a specified location. You can zoom in to a given level, a few other controls. So the example here at the bottom, and in a few slides, I'm going to show you a full Python code. The example at the bottom shows you how you can save a single image called frame000.png. So this is only for volumetric rendering, not for slices, not for projections, but for volumetric rendering. And then I'm calling the function iterator rotate. So that's function in the namespace of the camera object. And I access the camera object by simply using the scene and saying scene sc.camera, that gives me a camera object, and then camera.iterate rotation gives me a function that returns a set of snapshots that will spin my object, my visualization, by a given angle, in this case pi, 180 degrees, in 30 steps. So each step will give you a render that I save into an appropriately named PNG image. So frame for numbers and then .png. So of course, volumetric rendering is very expensive. That means that if you're doing lots and lots of these frames for a movie, then you probably want to parallelize it on a cluster, let's say. And currently, YT can do the following things in parallel. So for our presentation, I'm just going to give you a single example of parallel volumetric rendering on Cedar cluster. Okay. So, but of course, before you do that, you have to install YT on the cluster. So some time ago, we had a centrally installed version of YT module. I cannot find it any longer, so I don't think we have it. But fortunately, it's super, super easy to install YT into your own space. So what you do is actually all steps are given here. So you will use the Python virtual environment. Just log into the cluster. You load the Python module you want to use. So here I'm just saying module load Python, loading the default Python module. I'm turning on my, so I'm setting up my Python virtual environment. I'll just call it Astra. So that means that all the stuff I install into this environment is going to go into the Astra directory in my home folder. And then once it installs, so basically it installs just Python and some basic dependencies, things like NumPy. Actually, no, NumPy, sorry, is not part of it. So, but some basic Python, default Python libraries are installed. And then I activate that environment. So just say source in my home folder, Astra bin activate. And then I installed whatever I want. So for YT, parallel YT, you need Cython, NumPy, YT itself, and MPI for Pi. So that's the message passing interface library for Python. And then in normal use, just log into after you install it, you just log into the cluster, say source, activate your environment, then Python, and then you can run a parallel Python code. So here's an example of the Python code and of the Slurm job submission script. So these work exactly as I wrote them on Cedar cluster and also on Graham. Of course, you have to load the data set, so it already assumes that in the current working directory, you have the ANSO _64 data set unpacked into this directory. And what we're doing here is, so we are enabling, in the third Python line, we are enabling parallelism. So basically, we turn on MPI parallelism by MPI for Pi. We load the data set, we create a scene, we create a camera, we set up the resolution of the output image. So I want to have a fairly high resolution movie. So it's going to be a movie, each frame is going to be 1024 squared. And then I'm going to annotate the domains. So I'm going to show you the movie in a minute. So you'll actually see the outlines of individual subgrids, of the entire box. And then I'm going to annotate grids where you see the outline of individual subgrids. Then I'm going to save the first frame. Then I'm going to do rotation in 900 steps around the vertical axis, spinning the entire object in 900 steps by 180 degrees. And then each frame is going to be rendered and saved into an appropriately named frame for numbers.png file. So, and then at the bottom you see the script for running this. I'm going to run it on for 3 hours, asking for wall time of 3 hours max. I'm going to run it on 4 CPUs, asking for close to 4 gigabytes per CPU, and then of course you need to supply the count, your count on Cedar. And then I simply, in the script, activate the my AstroPython environment into which I installed YT and MPI4Py, and then I run the script with srun python-grids.py command. So I'm going to show you, so the sbatch command, you just submit the job with sbatch followed by the Slurm script name. And the performance you get, so I did a few runs, and I get about 1.5 frames per minute if I do it in serial. So it actually takes something like 40 seconds to render 1 frame on Cedar at 1024 squared. And then in parallel, it takes, I get more than 4 frames per minute. So that means that I have roughly, I would say, 70 to 75% parallel efficiency. So it's not exactly acceleration by a factor of 4, but it's still not bad. And then, so it will run in the background is a regular compute job on a regular compute node, not requiring any GPUs. So in parallel, it'll take a few hours. And then the output of this is going to be 900 PNG images. And then we have the FFmpeg tool installed right on the cluster, right on Cedar. You can use it to, for example, with these flags to create a QuickTime compatible MPEG-4 movie at 30 frames per second. And then this movie is sitting on the cluster, and then you just download it to your laptop, and then you view it. So I have a link. I put this video on Vimeo. You can actually click the link or type it in your web browser. And I'm also going to switch to, I'll try to play it back via this video conferencing tool. It'll be very choppy because it doesn't, well, high-resolution video doesn't translate very nicely into video conference software, but I still try to play it. And then if you want to have a high-resolution version, please feel free to play it on from Vimeo. So let me switch to the application window. So now I'm sharing my QuickTime player, and I'm going to play. So on my laptop, it's very high resolution. On your laptop, it might be choppy, but that's just the nature of video conferencing. So here we have 900 frames at 30 frames per second, so that it produces a 30-second long movie. So you can actually see the cosmic web structure, and you can see that there are more subgrids placed into regions where you have interesting physics happening. Okay, so let me switch back to the slides.
May I ask a question?
Yes, of course.
It seems like you are just rotating the box. The box is rotating. So the movie. So do we have time evolution of the simulation itself? Can we visualize that?
Yes, you can. Yes, in one of my last slides, I'm going to show you how you can load a time sequence. Absolutely, you can have evolution. In this case, I'm just loading a single. In this code, I'm just loading a single time step, and then I'm animating that by rotation. But for sure, you can have evolution as well. I'm going to show you an example of that.
And okay. Another question is, does YT read XDMF files?
Which one? Sorry, say again. HTML?
XDMF.
XDMF. I don't think so, but you can do that very easily from Python. Use the Python XDMF reader. So YT reads HDF5, right? Mm-hmm. But it reads not. Actually, I take it back. So it reads HDF5, and Answer, for example, uses HDF5 underneath. So XDMF is also an HDF5. It's a wrap around HDF5, just in slightly different format. So you should try. I don't know, but you can actually, what you can do, you can easily read XDMF into Python, put it into an array, and then supply the array to a YT object. And I actually have exact example of that in one of my slides later on, just not for XDMF, but for netcdf data.
Okay, good. Then I will follow that recipe.
Yeah, so the answer is yes. The answer is yes, you can, with a few lines of code.
Great, thank you.
Okay, so let me now switch to, actually, yeah, here we are, generic data. So that's exactly the example I was just mentioning. So in this case, I have a data set that I use for teaching visualization, usually pair view or visit visualization. So it's a netcdf data set that is just this mathematical function inside a unit cube, discretized at 100 cube resolution, and I just saved as a netcdf file. So YT by itself, my understanding, it cannot read netcdf. At least I tried, it could not. So, but what I can do is there are standalone netcdf readers in Python. So in this case, I'm using a library called netcdf4. And so I'm just saying import the dataset module from this library, or sorry, dataset function from this library. Then read the dataset, so it's a sign envelope.nc function. And then all is a pointer to this dataset. So all dot variables density subarray on that pointer will give you reference to the density array. And then you can subset it. So in this case, we're just subsetting the entire array. And when you do that, YT will produce a NumPy object. So in this case, the row variable is a three-dimensional NumPy array in Python. And then you can simply put that into a YT data structure. So the way you do this, use the Python dictionary, where you say that your field is going to be density, row field. Then you also need to specify the bounding box. So we're just going to say that my bounding box is going to be the entire computational box from entire domain inside entire unit cube from 0 to 1. And then I simply call the load uniform grid YT function that will take my dictionary containing the NumPy array and will create a proper YT object for it. And then I can simply use all the usual YT routines, so volumetric rendering, slices, projections. In this case, I'm doing the slice plot in the XY with the XY plane, going through the center of the box, plotting density, and you see that I get a nice slice with a linear color map. Okay, and so here's the same data set, but in this case, I'm just using the volumetric rendering. So again, netcdf data set, I put it into YT data structure. And then I create a scene. I use the transfer function, and for the transfer function, I just want to show these thin filaments. So the high density, well, actually they're not particularly high. Yeah, they're low density peaks. And I simply create a transfer function that has a single Gaussian peak at low densities, for a fairly wide Gaussian peak, now on a linear scale, not on a log scale that we had for cosmology, and then set the camera resolution, set the camera position, and then simply save that. So again, this takes some like 20 or 30 seconds on my laptop to do just this single frame. Okay. So here's a resolution of, here's an example of a multi-resolution data. So in this case, I'm actually not loading any data set. I'm just creating these data from scratch. So I'm just asking Python to create asking YT to create these four subgrids. So the level 0 grid is the base resolution grid, and then I have 3 additional high resolution grids. So all of them, all 4 subgrids, have a resolution of 32 cube. But then they differ in their placement. So the lowest resolution, the base cube covers the entire volume from 0 to 1, and then I have a few high resolution grids, all centered at the center of my volume. And then I go through all the grids, and then I set up a density field. So the way I set up a density field, so for each subgrid, I take its level, and then I compute 2 to the level, so that for the top of the density range for each grid is going to be, so for the base grid is going to be 1, then for the next grid is going to be 2, then 4, and then 8. And then I'm doing a slice plot here, so I actually created the YT data set. So you now use, instead of load uniform, what was it? Grid function, I use the load AMR grids function, into which I pass my Python dictionary containing these subgrids. And then it gives me a nice AMR data structure that I can still do all the usual things I can do with an AMR data set inside YT. So in this case, I'm doing this slice plot through the center, and you can see all four grids, and you can see that the density indeed goes from 0 to 8 for the highest resolution grid, right? Exactly the way we set up. And it's a random field, right? So just random field for each subgrid. And this slide just shows you that you can still use all the usual YT functions and objects for getting statistics of these objects. For example, you can cycle through all the grids, and you can print the density field wherever you want, on whichever grid you want, at which position. So position IJK indices. And here the last line actually shows you how you can print density at a given X, Y, Z coordinate inside the volume from whichever grids it comes from. Right? So you have full control over everything because it's Python, so you can just subset data in any way you want. So my final slide before the summary is the time series. So we had a question about how you can load a time sequence into YT. If you have a time-dependent simulation where each time frame is stored as a separate file, what you do is you simply use the same load YT load function, and you simply pass a Unix wild mask. So that's not the asterisk wild mask, but the question mark wild mask, where each question mark sign stands for exactly 1 digit, right? So you load all these files, you point YT to all these files in this exact format, and then when you actually start doing something with this data set, it will load the data. So you can simply cycle through all files in this data set. You just say put DS in this data set, and then DS will be appointed to each time step. So in this case, what I'm doing is I'm reading this data, and I want to do a plot of, so this is a cosmological simulation where you have structure forming, cosmic web, and galaxies forming. So I want to do a plot of the smallest density in the entire volume, entire simulation, and the highest density in the entire simulation as a function of, in this case, I just use redshift. So YT tutorials gives you time. I just wanted to do something different, so I have redshift on a log scale. So we are sitting at redshift 0, so just past the right edge of the box. And you see you have cosmic structure forming, so the blue curve shows the slow expansion of the universe, and then somewhere at around the redshift of 7, 8, you have the galaxies start forming, and then the red curve shows you galaxy formation, so high densities. Okay? And yeah, so that's all I wanted to show. And a bunch of things I didn't cover today because it's just a 1-hour webinar. So one important thing is data objects. In YT, you can create data objects, and the name is a little bit confusing, so it's not really clear what you mean when you say data object. So data objects, I found, is very similar. It is very similar to filters in ParaView. So data object basically lets you do some processing on your data, and the output is going to be a new object. So you can, for example, take a subset or include only points inside a sphere. So there's going to be a sphere object, right? And the output of that will only contain data points from whatever level of refinement of inside a physical sphere of a given radius and a given center. And so useful objects are surfaces that will let you plot isocontours. But of course, for isocontours, you can also use the volumetric rendering as well, and that will give you really fantastic pictures. So you can also use plot streamlines. You have to create streamline objects in YT, and if you're curious, just hit documentation, and it will show you how to do that. And yeah, so you can also work with YT from the command line, so you don't have to go into the Python shell. You can simply type YT commands from bash. And yeah, so working with unstructured grids, some of the data sets, sample data sets that I mentioned, a few of them on the YT website, they contain unstructured grids as well. So it's kind of useful, not from astrophysics, but from other applications. And it's kind of fun to work with them because they give somewhat differently structured data. And it's unstructured data, so meaning that X, Y, Z points can be anywhere. So you have to specify the position of the points, how these points are connected. So they're not necessarily regular rectangular grids. They could be tetrahedra or something else. And YT can just work with this data fine. So you can natively understand unstructured grids. And I think that's also now is the time for questions. So if you have a question, you can either type it, send an email to info@westgrid.de, or you can simply unmute yourself and ask a question via audio.
Can I ask a quick question?
Yep.
Will we have still access to this presentation after this session?
The slides, yes. So the slides are actually at the bottom. You see the link at the bottom? You can download the slides right now.
I saw it.
At the bottom of each slide, there's a link. So that will give you the PDF. We'll also put the slides on the, if you Google WestGrid training or WestGrid training materials, you will find a page where we put all the slides depending on whether it's visualization talk, an astrophysical talk, or bioinformatics or something. So just follow the navigation menu on the page. And the recording of this talk is also going to be added to that embedded video is going to be added to that page as well. But the slides are, you can just type in this bit.ly link at the bottom.
I just Googled WestGrid. Okay.
WestGrid training materials.
Okay. Oh, I found it.
Yeah.
Great. And I normally deal with HTML files. If I face difficulty, can I reach you out?
Absolutely. Yeah, just send me an email. I'll be happy to answer any visualization questions. Yep. Yeah, I can help you with
Okay. Thank you very much for your presentation. I really enjoyed it.
Sure. Thank you. Okay. Any other questions? If you have any questions in the future about YT or any visualization-related questions, just send me an email, alex.parasimov@westgrid.ca. And you can also send an email to support@computercanada.ca. And if it's a visualization question, then it's going to be most likely I will answer it as well. So.